Let's now put together all the different forms of energy we worked with in the algebra-based physics course. We use the third kinematics equation, along with the definition of gravitational potential energy, to derive an expression for kinetic energy, which of course is the energy of an object in motion. Kinetic energy is equal to 1/2 mv squared. Another type of potential energy was derived based on Robert Hooke's law. This gave the relationship between the force necessary to squeeze a spring together and how much it was compressed. That is called elastic potential energy, 1/2 kx squared. Both of these are forms of energy, and they are both expressed in joules. We can now solve problems using gravitational potential energy, kinetic energy, and elastic potential energy in 2 dimensions. This may seem odd because we know that energy is a scalar. However, different parts of the energy will be acting in different x and y directions. So we have to understand how these forms of energy depend on motion in the x and y axis. First, we'll start with gravitational potential energy. If an object is moving along an incline, does its potential energy depend on its displacement traveled along the incline? No, it does not. The change in gravitational potential energy, which is equal to mgh, where h is the vertical displacement or the y component of the motion, is the only thing we worry about. The inclined displacement is not important. Previously we used the letter d for that. D is in delta. We only care about the vertical displacement. How about the kinetic energy? Kinetic energy is a scalar. However, it relates directly to the velocity, and velocity is a vector. When we perform calculations of velocity, when we're given the kinetic energy and gravitational potential energy, we need to be very careful to relate the change in gravitational potential energy only to the change of the ke in the y direction. Thus, it only affects the velocity in the y direction. So you can change your kinetic energy in the x direction all you want. It will have no impact on the gravitational potential energy. What about elastic potential energy? Elastic potential energy is slightly different from kinetic energy. In this case, the amount that the spring is compressed is the important variable, no matter what angle your spring is set at. No trigonometry will be required to calculate that. Kinetic energy will then either use the vertical displacement an object covers, when we want to see how it relates to gravitational potential energy, or the actual displacement of the object from the spring's force, when we talk about comparing it to elastic potential energy. You might not be getting what this means yet, so we have to solve some problems. So we'll be using the conservation of energy, working some problems, and that should make this more clear.